Good morning, everyone, and welcome to the latest Motec webinar. Today's topic will be how to set up the ref and sync parameters. This seminar will be based on the 100 series software, which will also obviously work for the new M84. The parameters are quite similar in the older M4 and M48, but I don't refer to those two ECUs specifically. So if you've got any questions for those ECUs, you could probably put it up on the chat box. I have Dwayne Mitchell here to help me today, so if anyone's got any questions, they can type them in the chat box and Dwayne will see if he can help. We've also got a couple of other Motec employees here, so they'll be able to help on your questions. Topics for today are the software location, and by this I'm just basically showing you where in the software is the setup we'll be going through today. Some information on what ref sync triggers do I have, more or less identifying what you need to set up, ref sync mode, the crank reference teeth, tooth ratio, crank index position, sensor type, edge polarity, and the various filters. They're all the specific items that need to be set up in the ECU software, so we'll go through each one of them in turn. As for software location, if you have the M800 ECU Manager software open, or even the M84 software, the location is in Adjust, Sensor Setup, Ref Sync Sensor Setup, and then its main setup. It doesn't matter if you do this offline or online, you'll be able to set them up. If you're doing it online, it's basically a change straight into the ECU and you'll get instant results. If it's offline, then obviously you will need to save this as a new file and later on send it to the ECU. What ref sync triggers do I have? This is quite a broad subject and there is a reasonable amount of experience involved, but let's say you were ringing someone at Motec, perhaps myself or Dwayne, to ask what setup you need in the ECU. The kind of things we'll be needing to know are what is the pattern of teeth on the crank or cam, or specifically for today, you need the crank and cam. Most engines these days, I assume, will be dealing with sequentially injected engines, which will both have a crank sensor and a cam sensor with varying numbers of teeth. I've just given you a little bit of an example picture on the side there from a Toyota. That's actually a 36-2 setup. Might look like there's more than two missing teeth with that big long flat, but a bit of practical advice is looking at the actual tooth profile. It might not be exactly what the signal looks like when it comes out of the sensor. So you just have to be a little bit careful. I get quite a few people sort of ringing me, telling me they've got weird patterns, and from experience, I know are not true. So at some point, you are going to need an oscilloscope, or luckily enough, with the 100 series or the M84 software, we have the ref sync capture program. Another sort of simple thing is with Hall sensors with a nice square wave. If anyone's watched my last introduction to ref sync triggering, the Hall sensor switching profile, I suppose you'd call it, of the voltage may not be the same as the actual physical metal tooth. So looking at the actual physical teeth is just a start. You'll still at some point need to use either an oscilloscope or the ref sync capture to confirm exactly what the ECU is going to see, and ultimately that's what we're interested in. Just as a bit of an example there, I've just shown sort of what that magnetic signal will look like if we had the sensor on the trigger disc from the previous slide. That's our ref sync capture program in the M84 and the 100 series ECU software. It's located under Utilities and then Ref Sync Capture. Now we're moving on to the actual setup. So this is, like I said before, with the software location slide. This is in the actual main setup for the ref and sync. The ref sync mode is a number or an indication to the ECU of what pattern of teeth to expect. Now we have a couple of different sort of types here. The first one is what we would call a standard ref sync mode. Now these are pretty much what vehicle manufacturers would have been using maybe 10, 15 years ago until maybe the end of the 90s. So they're quite generic, and so we can write software that is relatively generic as well. Now with the ref sync mode number highlighted in blue there, you can see down the right hand side we have 0 to 9 as the different standard modes. So these are things like multi-tooth modes, where you just have like possibly 12 even teeth, or the simple missing tooth or additional tooth modes, like perhaps some of the Toyotas where they have a single sync tooth and 36 minus 2 missing teeth, again like the photo I had in the previous slides. All of these modes basically assume one single sync tooth. So that means there's only one tooth on the cam or maybe in the distributor. So these would be a standard mode. You just have to be a little bit aware that there's a couple of different types. You'll see the one, say number 5 there is one missing twice per cycle, and then number 6 is one missing once per cycle. Now that could be the difference between a 2-stroke or a 4-stroke. So you sort of have to understand how many times are we going to see this missing tooth in one cycle of the engine. So is the engine a 4-stroke or 720 degree cycle, or a 2-stroke, a 360 degree cycle? Now for any of these modes, if you press F1, you can get like some nice detailed help on what the pattern is expecting. I won't go through every little example. Obviously it's quite a big subject. For our OEM modes, now this is anything from 10 and beyond with the ref sync number. These are specific modes used by vehicle manufacturers. Now they do stretch back into the early to mid 90s with a few of the manufacturers like Bosch, but you'd almost guarantee there will be a specific OEM mode for most modern engines, especially something with a variable cam. They need both a fairly complex crank trigger, but to measure the position of the cam and also to sync the engine, they need quite complicated patterns on the cam as well. So to make sure the ECU recognizes this, we generally have to write a specific mode for a particular engine. Maybe, you know, the current model Subaru 2.5 litre turbo engine with variable cams. So again, without going through every single instance, if you press F1, you will get help and a bit of a description on each of those modes. Normally what would happen is you would probably contact your Motec representative or one of us here at Motec Research and let us know what type of engine, and we pretty much have the information that you need to get this up and going. The next parameter is the crank reference teeth, or basically the number of teeth on the ref. Now this is how many teeth per one revolution of the crank. And it's also the number of evenly spaced teeth. So if we have a missing tooth mode, we would include the teeth that would be there if they hadn't been cut off. And we would also, on a, say, a 12+1 setup, we would exclude the additional tooth. So it's the number of evenly spaced teeth that would be there, ignoring missing and additional teeth, and it's for one revolution of the crank. Now if I just go to the next slide, I have a few different examples there, just to a repeat of a couple of the key points there. So on the left, we have 12 evenly spaced teeth, fairly standard mode, so that number would be 12. The next one along, if anyone's got a Honda K20A engine, they have a 12 plus 1. So at the top there you can see basically a double tooth. As far as the ECU is concerned, it's 12 teeth. 12 teeth per one crank revolution. That's 12 evenly spaced teeth. And to the right, probably fairly common these days, a 36 minus 2. So they've machined 36 teeth, cut 2 of them off, but again, as far as the ECU is concerned, that is 36 evenly spaced teeth. The ref sync mode takes into account that 2 of them are going to be missing, or there's going to be a single additional tooth. And just a bit of an example where not to get tricked up, on a Nissan 360 optical, maybe like an RB30 motor, they have 360 ref teeth. But those ref teeth are on the cam, so that means 180 teeth per crank revolution. So the number of teeth, or crank reference teeth, for a Nissan 360, as far as the ECU is concerned, is 180 teeth per crank revolution. The tooth ratio, this is a bit of a hard one to describe, so I'll go through it briefly. This is more of a tuning type parameter where you don't really know exactly what the tooth ratio needs to be until you have the engine ready to fire up. Now this tooth ratio parameter is only set when we have additional tooth modes like our 12 plus 1 or our missing tooth modes like our 36 minus 2. And it effectively sets more or less a time limit for the ECU to decide whether it had a missing tooth or an additional tooth. So on my diagram below, the top line, let's say that's a 36 minus 1 in this case, and our tooth ratio is 42. So effectively, the ECU knows the basic time between 2 evenly spaced teeth, and we're saying that if we have that time plus an extra 42%, we have not had a tooth appear in that time, then we will declare the missing tooth, and that works for our ref sync mode. It's a similar idea to the lower one with the additional tooth, but this time we're basically saying that the tooth comes less than 42% too early than what the ECU would expect for the normally spaced teeth. So it's just a way of the ECU deciphering whether it's actually seen these additional or missing teeth. The numbers, you see there's 42 in my example. A good rough guesstimate would be you would be around 40 to 50%, but this will need to be tuned based on the engine. But most of the time you will find it fires up with the standard setting and you don't need to worry about it too much. Crank index position. This is probably one of the most important settings in the ECU. I'm going to spend a few slides just going through this. Basically, this ref and sync trigger tooth system, the ultimate idea is to let the ECU know exactly where the crank is in its cycle so that it can place spark and fuel at the right time, also know RPM, etc. So everything to do with timing events against the crank trip is very important. So the example I've given here is a missing tooth mode, and basically for missing tooth mode, the index tooth, that's the index tooth in our crank index position, the index tooth is the tooth that happens at the end of the missing tooth gap. So you can see where the little blue arrow is pointing there. The index tooth is the one that happens after that. The way the ECU decides which of the missing two events to use is to use the sync tooth circled in blue there. So basically the missing tooth event that happens after the sync tooth, that's the index tooth. So we need to know how far in crank degrees before top dead center compression number 1 does that index tooth happen. For a two-stroke engine, it's going to be nice and easy because you don't have the sync tooth because everything happens in 360 degrees. So basically your crip for a two-stroke engine will be how far does that index tooth happen before a top dead center number 1. They're all compression. A couple more examples, and it's probably a good idea to go to our website and view my introduction to ref sync if you haven't already. This is just a bit of a repeat of that. Just to give you an example, the top one there is an even tooth mode where the index tooth is the one that happens straight after the sync. And on an additional tooth mode at the bottom there, it is the index tooth that happens just after that double tooth. So when working out the crip, it's a simple matter of finding your index tooth and how far does that happen before top dead center compression number 1. The crip number is in crank degrees. It's not a special calculated number or any kind of computer programmer number. It is in crank degrees. Now if I go to the next slide, I'll just give you a basic run through of if you were going to try to work out this crip on the physical engine, here's how you do it. Now for a 4-stroke, as I mentioned before, we're going to have this sync tooth because the crank goes around twice in one cycle. So if we wind the engine over until the sync tooth lines up with its sensor, now on most engines you might actually have to pull the sync sensor out of its mount so you can see the sync tooth. So you line the sync up with its sensor and then start turning the engine in the running direction. So we're not turning the engine backwards, not calculating any numbers backwards, it's all in the running direction. So start turning that engine over, and now we need to focus on the ref sensor. What we want to do is go to the very next index tooth. So on our even tooth, it's the very next tooth on the crank. On the missing tooth, it's the very next missing tooth event. And on the additional tooth, it's the very next time we see the double tooth and then sort of one more ref tooth past that. So once we've worked out that the index tooth is lined up with the ref sensor, effectively we are at 0 degrees crip. So the number you need to enter in as the crip for the ECU is how many crank degrees from where the crank is now back to top dead center compression number 1, and again always turning the engine in the running direction. At this time we don't have to be super accurate because, as I'll go through in later webinars, as long as we are within the ballpark of something that the timing light can see, then we're pretty right. The next parameter is the ref and sync type. So what sensor are we using for the ref and sync? So again, referring to my previous webinar, we need to make the decision on do we have a Hall or a magnetic. So the Hall is our nice simple switch sensor where it has 2 states, either high voltage or low voltage. Again, we're not too worried about exactly what those voltages are as long as they meet the criteria of trigger voltages in the ECU. Again, my previous webinar. The magnetic is a analog AC voltage. That's the diagram at the top on the right there. We also have an extra setting for logic level. This is basically a Hall type signal, but it's where the sensor doesn't need like an internal pull-up in the ECU. These are quite uncommon these days, so it's quite rare that you'll actually see them, but I probably have to mention it since though it's there on the screen. Next parameter is our edge polarity. So of the signal, we need to tell the ECU specifically which part of it to use. Now, for a Hall sensor, we have a nice even or nice simple switch on or off. So as far as the ECU is concerned, the square wave rising voltage going from low to high, or falling edge voltage going from high to low, they're equally valid as a signal. But we have a little bit of a more or less a logic type sort of problem here, where we have to be a bit careful in choosing our edges, because what we don't want is we don't want two edges that line up perfectly, especially on an even tooth mode. So in my diagram below, you can sort of see that the falling edges of both the ref and sync line up almost perfectly. Now, if you consider that in an engine, a mechanical system, there's going to be some slop between the crank and the cam, so that's going to move around a little bit. So in my table up to the left there in the middle, you can see that I've said that using a falling edge on both the ref and sync is definitely not recommended, because if those two line up, it's a bit of the chicken or the egg scenario. The ECU has a hard time in working out exactly which one happened first. So it's not a great way to do it. That doesn't mean to say we can't use the falling edge of either. It's just the combination. We don't want a combination where the combination of edges lines up perfectly. That's just not going to work. It's going to cause misfires. So we can choose any other combination there, all the valid ones with yes next to them. I'll let you at a later time rewatch this and maybe pause and have a bit of a look at that. But it's the edges that line up evenly. We don't want to use that combination of those two edges together. It just won't work. Just as another one to have a look at, possibly once you rewatch this webinar, is that if we have a missing tooth event, and in this case I've got a fairly long sync signal there, you don't want to use a sync edge that falls within the missing tooth event. That can cause problems as well, again with teeth moving around. It's actually something we kind of see fairly often on some of the motorbike engines these days. So you have to be a little bit careful about choosing the sync edge in that case, because you don't want the edge that falls within the missing tooth event. So you can see there I've said for the sync in my little table there, for both the syncs with the falling edge, it's not recommended. I say not recommended as in it will work and it may not cause problems, but in practicality I would say don't do it, because it can cause you a few issues. Now, for magnetic edge polarity, a magnetic sensor gives a specific signal depending on how it's wired. Now, unlike the Hall sensor, you cannot choose which edge. The edge you have to use is set by how you've wired the sensor. So taking the top diagram there, we've got a rising edge. So the sensor voltage comes down into a negative, and then as the tooth goes past, it shoots up from negative to positive, and it's the edge that is the cleanest crossing of the 0 volt line is what we want. So you can see in that one, that's a rising edge. Now, the same sensor, if we unplugged both wires and swapped them around, the sensor would still work, but this time the polarity of the magnetic signal would change to a falling edge. You can only tell this information by using either our RefSync capture program or an oscilloscope, but you have to tell the ECU the right edge. If you get it wrong, it will cause misfires. The engine may not sync up, it just won't work. So very important for a magnetic sensor, you have to get the right edge polarity. And again, like I've been saying, this is quite a big subject, but I'll give you another little bit of an example similar to our hall one before, where I have the sync edge and the ref edge lining up. Now, both of those signals, they have to be falling edge because that's the way the sensor's wired. If you have those edges clashing, so as I said before, you can't have the ref and sync happen at the same time, we have a fairly big problem here, because if I rewire, say, the sync sensor, all that's going to do is invert the signal, but it's still going to have the crossing of 0 volt line up in the same spot. With a hall sensor, you've got this square edge and a rising and falling that are effectively the distance apart, the same as the length of the tooth. In this case here with a magnetic sensor, our only option is we physically have to move either the ref sensor or the sync sensor to move those signals apart. Choosing a different edge or rewiring the sensors in the opposite polarity is not going to fix the problem. So in this case, it's a physical, mechanical movement that is the only way you're going to fix this. As we are Motec and we don't like people to have to change too much on a standard engine, one example where we've needed to add some software is our ref and sync trigger voltage. Now the scenario here is if you had say 100 series ECU and you actually piggybacked it onto a factory ECU. Now generally you'll only see this with magnetic sensors, but inside the factory ECU, maybe the sync sensor is slightly pulled up. So by that I mean that its resting voltage without the crank turning or the cam turning, the voltage on the, let's say, sync wire is not at 0 volts. It may be at 1 volt. So what we have to do is instead of looking for the cleanest crossing of 0 volts, in this case, we need to look at the cleanest crossing of a higher voltage. So in the ref or sync trigger voltage, I can say put 1 volt there. So now the ECU is looking at the most clean crossing of 1 volt instead of 0. Now, you should never need this parameter unless you have a spliced signal or a piggyback. If you have this kind of behavior on a standalone Motec installation, so there's no other ECU connected, then I would almost guarantee that you have either a wiring problem, or one of the other common things is people accidentally say that the sync input is a hall sensor instead of a magnetic sensor, and that of course will turn on the internal pull-up. Again, back and watch my previous webinar on the ref sync for a better understanding of that. But just remember, if it's a standalone Motec, you have to leave these at 0. Next we have the filter table. Now, the ref and sync filter tables are a time-based filter. So they're there to get rid of any invalid signals that are of a certain time or less. So if you have a look at my diagram on the top right there, that's a fairly classic example of some ignition noise. You can see that the actual ultimate voltage of that signal is higher than the valid signal being right in the middle. So we can't really filter this any other way other than time. So luckily, like an ignition spike like that would be of a exceedingly short amount of time compared to our actual valid signal. So the idea here is that we have a filter which varies based on RPM, and we can put in a maximum time, or a time that says anything lower than this, just ignore it. Now that's in microseconds, and as a practical bit of advice, the smallest amount of filtering for time-based is often best. If you press F1 again for this table. It will give you some calculations based on tooth counts. So I suggest it's probably a good idea to read that. But in all practical sort of examples, I would suggest that you would lower this to the minimum amount. If you lower it too far, obviously it's going to cause problems. But if you can get away with it and drop it by, say, 20 here, there, and everywhere, I would suggest doing that. The next table we have is the mag sensor level table. Now, this is a filter again, but slightly different to the time-based filter, and this is a voltage level filter. Again, in my diagram to the top right there, you can see towards the beginning of that trace, there's a small signal. Maybe that's a, I don't know, a machining problem with the trigger disc. But compared to the valid signal, it's a very short, very low voltage. It might actually, they could end up being like quite a long time. So the time-based filter may not get rid of them. But here we can see that if I set my voltage level to be well below the maximum level of the valid signal, but higher than the actual spike or problem, then anything below that blue line is going to get ignored. Now the suggestion is that we want that voltage level to be 25 to 30% of the valid signal voltage, and that's about right. Again, it varies with RPM, so you might need to do a few different ref sync captures at different RPMs just to get an idea of how the voltage builds. And again, for a bit of practical advice, you can see in my table down the bottom, I have a maximum of 2 volts filtering at 3000 RPM. In my own experience, about 2 volts is probably as much as you need, but again, it can depend on the car. The ECU itself actually clips all magnetic sensor levels at 9.8 volts. So 25 to 30%, yeah, about 2.5 is probably all you should need. If you need much more than that, I would probably make the suggestion that your wiring is not as good as it could be, and maybe you're running the ref or sync wires a little bit too close to your ignition system or something, dragging a lot of current. So just keep that in mind. Okay, that's about the end of my seminar. I hope that's clarified some pointers for everyone. There will be future ref sync webinars. I'm going to do this a fairly broad subject, as I said, so the next one will most probably be on a bit of troubleshooting and ref sync sort of problems when you're going to start the engine. So between the 3 eventual webinars on ref sync, I hope I've presented pretty much all the information you need. All of these webinars are, of course, recorded as normal and will be put up on our website for you to download and watch a few more times. Also, it's always a good suggestion to join our forum on our website. There's plenty of people around the world on there all the time, so if you've got a fairly urgent question and maybe it's midnight in Australia, it's probably an idea to jump on the forum and just put the question there. Maybe you'll get like an instantaneous answer there. Okay, thanks everyone for attending, and look forward to turning up to our next webinar. Thank you.